Right. So first, but the goal is to try and tell you something interesting that you might want to talk to me about, and I picked some stuff. Also, like, why am I here? So I figured I'd start with that very quickly. There are like kind of things that drive me to study a particular problem. A bunch of it is structure, unearthing structure and really leveraging it, not leaving it behind on the table, which will sound extremely familiar to people here. I'm interested in productivity, largely developer productivity, largely productivity of some developers who are willing to let go of current processes of software development and look at really different ways of doing things. The ones who must remain within their confines of their current development processes, I'm not interested in. Somebody else can worry about them. And I really, really like conceptual integrity and conceptual clarity of the stuff that I do. And if my explanations are no good, I keep working because it doesn't satisfy me. Again, that's not so unfamiliar. I've got some weapons. Math being the first one. Math and structure in this corner. Why am I here? Right. I do like N algebra. So category theory to me is one algebra. But what makes me a little different than most from a mathematician's point of view is I have a rather large toolkit of analysis and of geometry that I also use, which is less used in computer science. That's going to come up a little bit. I like to use language. Like syntax to me, not is it pretty, but there's a lot of stuff you can dig out of syntax. If a human being is bothered to write something down, don't ignore it. Take the structure that's there and use it. So I'm not a diehard semanticist. And connected to the productivity bit, there's a lot of stuff you can dig out of linguistics as applied to programming languages, but I'll get to that later. And in computer science, I've got a bunch of weapons, and some of it will come up, not all of them, but just really quickly, Kolmogorov complexity, symbolic computation, metaprogramming, and the latest thing, Curry Howard on steroids, or computational trinitarianism. Wow, I actually managed to say that. Anyways, so we dig into actual stuff now. So first topic, I want to tell you a tiny little bit about piecewise defined functions. Something that looks like, say, and minus x, x, and am I going to, yeah, do it this way, x goes 0. So for most of you, this is the absolute value function, and part of the question is, I give you two piecewise defined functions. Are they equal? Can you normalize them? And the old algorithms, and so here, this function here has one breakpoint at 0. And in general, you can have a bunch of breakpoints. And the old algorithms were exponential in the number of breakpoints to figure out are two functions equal. And the reason they were is that they embedded the normalization procedure into the arithmetic of the codomain. So you can code up this problem as a problem of arithmetic, and it blows up. The key to seeing things differently is to notice that when you're evaluating such a function, you're using the domain twice. Once over here to make a geometric decision. You're leveraging the geometry of the domain space, and you've got a partition. The partition part is really important like the partition idea here is kind of what makes everything generalized nicely. And then if you query this, first you make a partition decision, which gives you an index. The function that you're left with, and here I made it was total, but things like 1 over x and so on, you can change things so that all of a sudden, all the functions you're dealing with are total, because you can be dependently typed and you're fine. But the really key idea is that like of a two-phase evaluation, and your first phase is a partition that leverages geometry. And if you've done enough optics and you recognize a prism here, good for you. Yes, that's what it is. And once you've done this, then you just unwind everything and you get a linear algorithm instead of an exponential algorithm. Because partition, like yeah, they're after that it's easy. Idea number 2, more structure. Kind of all know that the integral from a to b of f plus the integral from b to c of f is the integral from a to c of f. I won't write out all the decorations. Fine, whatever, blah. What's interesting about this is that, erase it, A, B, C, or A, B, C. It all works. It doesn't matter. Like, no matter how you want to work it, it's always correct. This is universally true. It just doesn't matter at all where A, B, and C are. Oh, that's kind of fascinating. Like there's something weirder going on, and it's even more fun when you start like A, B, C, D. What's going on is that over a certain period, like area, you are doing some work, undoing that work, and doing it again. If you remember the lesson of partitions here, geometry, and you do the same idea again, you realize that you've got a +1 multiplicity here, a -1 multiplicity here, a +1 multiplicity here, +1, +1. If you first resolve the geometry, you realize that you can do this, then this, then this, and you don't have to do the extra work. And of course, it's all going to work out. It doesn't have to be just for integrals. It can be for anything that it's easy to prove when the underlying operation that you're doing is invertible. If you're careful enough, you can actually make sense of things like this, even for products where you don't really want to be dividing by 0. And this is where the currying really, really matters. You kind of have to first resolve the geometry and then say, okay, I'm going to define the semantics of my operation to be the value that you get once you've forgotten all of the useless work that you shouldn't have been doing. And all the theorems work out. Is this the correct semantics? Well, that's interesting, because you've just erased some division by 0. Or, so even in this situation here, if you go back and you create a function which is actually defined here by some f, and is actually undefined here, you can ask yourself the question, does this even make any sense? Like I've evaluated a function where it's completely undefined, except that over here, you've evaluated it exactly 0 times. Does it matter that you know, does it really matter? So there's a non-trivial question of semantics if you're going to do it this way. So underneath this, there's something called hybrid sets, where multi-sets with multiplicity in the integers. It just works. You just unravel all the stuff that you normally do with multi-sets, and you just swap out n for z, and there's no real difficulties that arise once you do that, except for the fact that, like, what the heck is a set with negative multiplicity is kind of philosophically kind of interesting. If it is merely a record of, oh, I'm not going to actually do this work, it's not so bad. Okay.
So a few people in the chat are complaining about the whiteboard. I don't know if it's possible to fiddle with the focus, maybe because it's very blurry, or maybe at least turn off the lights would help.
Yeah, there is like glares.
Maybe not for you in the room, but
yeah, it's not really the glare, it's the focus.
Yeah, mostly it's the focus. Yeah, that doesn't really help.
Just hit the camera a bit.
The camera is a laptop, I imagine.
Yeah, hit the laptop.
So not much we can do.
But you can move it slightly, maybe.
You could try closing the blinds.
And I thought it's drinking.
The less light there is, the harder it is to focus. Yeah, but then we put the lights on.
Yeah.
Yeah.
It's almost like exactly like prescription lenses.
Yeah, I think it's better with the lights.
Really? I mean, I think you're fantasizing.
Yeah, so I don't think we can do much about the focus. So let's keep it like this. It's legible, barely, but yeah.
Yeah, sorry. Maybe
there are some questions in the chat if you want to answer them.
Sure.
Do you want me to read them, or can you see?
I can show them to you.
Right
here.
Free abelian group. At which part was that question about?
I think Vikram
Yes.
gave a longer version of the same question.
Are you using multi-set language? That's a longer conversation I'll had. Hybrid sets like free abelian groups, yes. Basically, yes. And the paper was, trying to avoid category theory and all advanced explanations, but do it all in the weeds, because you don't need. So there's a paper about hybrid sets, and there's no need to bring in all sorts of advanced stuff. Just like take your multiplicity in Z, and it's simple. There's no need to go full stuff. Yes, there's probably a very fancy explanation that works too. That wasn't the paper we wanted to write. Let me move on to something else. Let me call it modern tagless. So Ken, Oleg, and I are really quite annoyed that our pun on funneling tagless actually became the name that our stuff was labeled with. But anyways, if you look at what's in the paper and what people have done, there's a bunch of ideas that somehow seems to have been missed about what's going on. So what's the heart of the work in finally tagless is that your abstract, if only I could spell, over representation, and I'm going to use the Haskell notation of a language that you're trying to represent. So you really are quantifying over a type structure, and you're basically saying, okay, I don't care about the actual representation, one, and two, you represent your language as an interface. So, sometimes you represent your language by the interpreter via some smart constructors, or you represent it as a data structure. The third way is representing it as an interface that's typed over a representation. And this allows you to do multiple interpretations of the same syntactic construct. And because it's an abstract interface, it allows you to do both semantic interpreters like evaluators and silly syntactic ones, like counting how many symbols you have in your program is an interpretation that you can do in tagless. So it keeps all of the intentional information around. The other thing that hasn't been really noticed is there's a certain modularity that you can have in how you specify your language. It is what kind of interface are you giving? You're actually giving your language as how to fold over your syntax. It's not quite a church encoding. It's Scott Mogensen encoding, which is ever so slightly different. At the higher levels, it comes in. But basically, if you understand it as a church encoding, it's kind of okay. And what you end up encoding are introduction elimination pairs for each of your type constructs that you're interested in. And because they're interfaces, if you have a nice host language that has coproducts of interfaces, which Haskell kind of allows you to fake, then you can be modular. If you're in a poor language that doesn't have much of a language of interface, and all you can do is like include in, say, OCaml, then your modularity in this way of doing things is not so good. The other thing to notice, since I'm here, is the phrasing of the introduction elimination pairs that you use is old style type theory. It's not at all bidirectional. And I have no clue how to use the interfaces of current programming languages to embed a bidirectional type theory in there to piggyback on my language. I just don't know. Somebody here knows, tell me. That would be super cool. I think the answer is that currently, without serious gymnastics, can't be done. And lastly, I'll write it here and because like partial evaluation and meta programming, most people have never gotten to the part of the paper about partial evaluation. And certainly the way we wrote it, we completely missed out on the modularity. This is why I'm talking about modern of partial evaluation. It is possible to couple an interpreter, a compiler, and some equational theories in a modular way. In fact, if you have a compiler that's actually written as in a very particular way, you don't even need the interpreter. But it is possible to write a partial evaluator that really looks like take this and use the equational theories to combine them in this particular way, and poof, you get a partial, like an optimizing compiler. You get a partial evaluator, and you can see in your code where the optimizations come from. They're staring at you in the face. That's the thing that just pops right out. And so, of course, OHAD is in the audience. Frex is your gift here. Frex is like comes right in and makes your life even easier about this part. I still don't know how to do NBE in the same really nice way that like when you're staring at your code, the nice part is why do your optimizations work? They're like staring at you in the face. Whereas in most compilers, that's really hard to see. So at some point I should like write up a modern tagless paper, but I haven't gotten around to it. And Ken and Oleg have moved on to other things. Right. Is there any questions on that? Apparently not. Okay. So that's a whole lot about structure. I should tell you a little bit about dev productivity. Oh, actually, I'm doing better than I thought on time. I went into a hyperactive mode. So I've got a project called Drizzle that you can find on GitHub. And the point of that, like the motto of Drizzle is generate everything. So unlike this work, which a lot of it is focused on structure and leveraging it, this work is really a piece of engineering focused on developer productivity. The underlying, what makes it work, like are some observations. If you look at a piece of software, go on GitHub and take a piece of software that's really well built, that has a lot of documentation, it's been used for a long time, and you look and there might be some, especially if it's research software, there might be some theory and specifications and design and tests and build scripts and all of these other things. And if you read all of these things, one of the things you might notice is that all of these documents, including code as a document, are talking about the same thing, which is not surprising because it's one piece of software. So at an abstract level, the knowledge that's embedded throughout all of these artifacts is actually much, much smaller than the stuff that human beings wrote down. So I told you, chromograph complexity is one of the things that drives me. And so when I see a whole bunch of information duplication, I think, aha, how can I write a compressor for this? My ideal compressor is always a meta program where I want sort of an encoding of knowledge as input and splay out everything as the output. And so that's kind of the underlying driver of Drizzle. Does this idea work? If we do that for any kind of software, that's sheer idiocy. Of course it won't work. However, there's a category of so-called well understood software, where the science and engineering of that software is decades old.
Maybe this is a stupid question. What does productivity mean?
I have a paper on that too. The short of it is, so if you take the old definition of productivity from the 1900s, which applies to manufacturing, that drives you down to, how many bits can you do in an hour? Like how much work can you do in an hour? And it's relating labor input to output, usually measured over a very short period of time. If you look at IT and you look at some of the business stuff that has been done about the productivity of IT workers, the one thing you notice is a lot of their work is better measured over 1 year, 2 years, 3 years, because a lot of their activity is about process improvement. Like there's all sorts of things that if you measure it on too short a time scale, you end up trying to count the number of lines of code per hour, and that's just idiotic, right? So, but if you look at the value produced over a long period of time by an organization, that can give you a stable notion of productivity. And so I'm very interested in productivity that happens over projects that are 10 to 20 years long. I don't care about 1 month's productivity. Somebody else can worry about that. I just don't give a.
Sure.
Good, great question. I love that question. But this is where, people have just seen my philosophical bent come right out. And whether you care, I don't know, but I do. Right. So well understood software and long time horizons. So 10, hopefully plus at least 10 years, preferably 20, where when you start, you want your software to be around for a long time. And there's a lot of software that's like that. Software that goes in a space probe that goes out there. Even software that sits in a whole bunch of medical software that they embed into people. They really don't want to push software updates to you, especially like to a pacemaker all the time, although they can, and it's scary. Anyways, there are pieces of software that really do live for a very long time. And those are the ones we're kind of trying to really capture. And I'm just looking very quickly at my notes. So yes, it is true that there is actually a very small amount of information in most software. It can be encoded into a small database of facts, especially when it's a lot of the stuff like relies on pretty darn basic physics. F equals ma can be leveraged a lot. Like there's a huge amount of software out there where fundamentally one of the crucial explanations for why it works boils down to F equals ma. And that's one equation that you write down once. Just the fact that it's in some sense expanded out into thousands and thousands of pieces of software is a waste of productivity. One of the key things to make this work, so like this is also force equals mass times, and I'm going to cheat here to make a point, change in velocity. And I know this is not going to be readable, but I said it out loud. So this mathematics has a clear correspondence to a piece of English. So what we use are something we call tri-form theories that have a syntax. You see it here. That has a semantics. So we don't leverage that nearly enough yet. These two are related by what we call meaning functions, sometimes meaning relations, and then basically English. You can think of it as there's a Haskell framework for doing languages, grammatical framework. We're actually going to switch our awful homegrown English sentence mangler hopefully to that. But basically, if you write down like that, this is force, and force has particular units, and mass can only apply to certain things. You end up with a type system, not just of units, but of what applies to what. And so you can check that, and you unwind all of that, generate everything. And you can end up generating specification documents that are really, really long, that read like no human would ever write that out because it's too detailed, but it's okay because it was like the command of knowledge that you need to encode, you only encode it once. Of course, the thing that weaves together the artifacts is still a program. It's just weaving a program out of quite different bits than you usually do. We have a backend called GOOL for generic object-oriented language. I'm in the wrong place to talk about OO. I despise OO myself, but because our target market likes things like Java and Python, fine, whatever. So GOOL is a meta language from which we can generate Java, C++, C#, Python, Swift, and Lua. When you write such a thing and you actually write a pretty printer to all of these, it's great fun because you definitely see that Java and C# are the same language. Oh my God, those two things, there's so much the same language, it's ridiculous. The pretty printers between those two share almost all of their code. Swift is odd in places, but it's not that different. We're trying to add C and MATLAB, and that's harder. They're weirder. And the key, okay, so what GOOL does is it generates well-formatted, fully documented code. And so because we have all of this information, we can label everything with what it is, because not only do we know that F is force, we actually have a definition of what a force is. And so we can hyper document the code and format it so that a human being can read it. So if somebody wanted to take the output of this generator and actually just look at the code, it almost looks like a human being wrote it. And once you have this information, doing that is actually not hard. You just have to have the right stuff in your back pocket to do that. Right. Yes.
Sorry, very superficial. Reminded me of the Inform language for writing interactive fiction.
Yes. So internally, we have about 15 DSLs embedded in Haskell. And so some of them are closer to that, and some of them are much more like math. And so there's a whole bunch of different kinds of knowledge that we need to encode. And so we have different DSLs to do that. And we're still kind of figuring out exactly what we should be doing there. But yes, so literate programming on steroids, Inform 7, all of these things kind of influenced us. Unfortunately, the current encoding doesn't look like English enough. We could have, like, our DSLs are embedded in Haskell instead of being external, because we want to be able to change them faster, and we don't want to be writing parsers left, right, and center. And since I'm here, we use classy lenses left, right, and center to get lots and lots of polymorphism, so that we can be abstract over the exact representation of everything. And that's really, really nice as a technology. Right. Oh, good. I'll actually get to the last. So this is the one bit where I wish I was not doing a whiteboard talk, and I could show you a whole bunch of slides and show you a demo and show you a lot more. But I decided, fine, let's try it anyways. Okay. And then moving on. Yeah, there was no questions on that. Last is theory combinators. Really, I should be precise. Theory presentation combinators. So again, back to syntax. You need to be able to write down what is a monoid. And once you've written down what a monoid is, frequently you'll want to write down what a commutative monoid is. And as a presentation, like a piece of text, what you've done is added an axiom, commutative. And there is a way to get from commutative monoid to monoid by just dropping a piece of information. So in the category of presentations, this is actually a display map. Similarly, you might be interested in idempotent monoids, and similarly, you get a display map here. And because they're display maps, or if you want to see it the other way around, it works too. This is the codomain federation for that category. There is indeed a pullback, and the pullback is idempotent commutative monoids as a piece of text. And the reason to see it as a pullback is that dropping an axiom is easy. Adding an axiom is hard because everything goes weird when you try to add new stuff. So if you look in most works on specification theory, they work with pushouts because they actually try to be incremental and build stuff. The stupid thing is, yeah, you just move to the, but they have weird restrictions, like the big restriction is one name, one concept. So what? So this is where in libraries, Coq, Agda, all sorts of places, you end up with things like monoid and additive monoid. What the bleep is an additive monoid? An additive monoid is a monoid where you've decided to use a symbol plus instead of symbol times. In your category here, you have renamings. Renamings are one of the most fundamental operations that we have up here. But if you do your theory wrong, you don't have renamings. They're not an operation that you are able to do on, whether you want to call them interfaces, Haskell type classes, Scala traits, signatures in ML, record presentations in Agda, whatever. You don't have these operations available to you in the theory in a nice enough way. And this is stupid. Like, you here in this room have heard about renamings all the time as being so incredibly basic as an operation in theory. And you can't lift that in a nice way to operations on combinators. So once you give yourself renaming, substitution, your display maps, your pullbacks, and actually your Cartesian liftings. So if I don't have a display map but a generic morphism here, then I get mixin for free. And you end up building a nice lattice of theories that works just fine, full of squares, like diamonds. Diamonds are normally hated in software. That's because the diamonds at the level of implementations are evil. The diamonds at the level of interface combinators are beautiful. They are what you want. And we don't have them yet. That's really badly missing. So all of the beautiful semantics that exists in our syntax for the language of theories, if you look at it, it induces a set of combinators for presentations. And we don't have these yet. That's just downright silly. And I will stop here.